A synthetic diamond is diamond produced in an artificial process, as opposed to natural diamonds, which are created by geological processes. Synthetic diamond is also widely known as HPHT diamond or CVD diamond after the two common production methods. While the term synthetic is associated by consumers with imitation products, artificial diamonds are made of the same material. In the U.S., the Federal Trade Commission has indicated that the alternative terms laboratory-grown, laboratory-created, and manufacturer name created would more clearly communicate the nature of the stone. Numerous claims of diamond synthesis were documented between 1879 and 1928. Most of those attempts were carefully analyzed, but none were confirmed. In the 1940s, systematic research began in the United States, Sweden and the Soviet Union to grow diamonds using CVD and HPHT processes. The first reproducible synthesis was reported around 1953. Those two processes still dominate the production of synthetic diamond. A third method, known as detonation synthesis, entered the diamond market in the late 1990s. In this process, nanometer-sized diamond grains are created in a detonation of carbon-containing explosives. A fourth method, treating graphite with high-power ultrasound, has been demonstrated in the laboratory, but currently has no commercial application. The properties of synthetic diamond depend on the details of the manufacturing processes. However, some synthetic diamonds have properties such as hardness, thermal conductivity and electron mobility that are superior to those of most naturally formed diamonds. Synthetic diamond is widely used in abrasives, in cutting and polishing tools and in heat sinks. Electronic applications of synthetic diamond are being developed, including high-power switches at power stations, high-frequency field effect transistors and light-emitting diodes. Synthetic diamond detectors of ultraviolet light or high-energy particles are used at high-energy research facilities and are available commercially. Because of its unique combination of thermal and chemical stability, low thermal expansion and high optical transparency in a wide spectral range, synthetic diamond is becoming the most popular material for optical windows in high-power CO2 lasers and gyrotrons. It is estimated that 98% of industrial-grade diamond demand is supplied with synthetic diamonds. Both CVD and HPHT diamonds can be cut into gems and various colors can be produced: clear white, yellow, brown, blue, green and orange. The appearance of synthetic gems on the market created major concerns in the diamond trading business, as a result of which special spectroscopic devices and techniques have been developed to distinguish synthetic and natural diamonds. Traditional diamond mining has led to human rights abuses in Africa and elsewhere. The 2006 Hollywood movie Blood Diamond helped to publicize the situation. Consumer demand for synthetic diamonds is increasing, albeit from a small base, as customers look for stones which are ethically sound and are cheaper. History. After the 1797 discovery that diamond was pure carbon, many attempts were made to convert various cheap forms of carbon into diamond. The earliest successes were reported by James Ballantyne Hannay in 1879 and by Ferdinand Frederic Henry Moissan in 1893. Their method involved heating charcoal at up to 3,500 degrees Celsius with iron inside a carbon crucible in a furnace. Whereas Hannay used a flame-heated tube, Moissan applied his newly developed electric arc furnace, in which an electric arc was struck between carbon rods inside blocks of lime. The molten iron was then rapidly cooled by immersion in water. The contraction generated by the cooling supposedly produced the high pressure required to transform graphite into diamond. Moissan published his work in a series of articles in the 1890s. Many other scientists tried to replicate his experiments. Sir William Crookes claimed success in 1909. Otto Ruff claimed in 1917 to have produced diamonds up to 7 mm in diameter, but later retracted his statement. In 1926, Dr. J. Willard Hershey of Macpherson College replicated Moissan's and Ruff's experiments, producing a synthetic diamond. That specimen is on display at the Macpherson Museum in Kansas. Despite the claims of Moissan, Ruff, and Hershey, other experimenters were unable to reproduce their synthesis. The most definitive replication attempts were performed by Sir Charles Algernon Parsons, a prominent scientist and engineer known for his invention of the steam turbine. He spent about 40 years and a considerable part of his fortune trying to reproduce the experiments of Moissan and Hannay, but also adapted processes of his own. Parsons was known for his painstakingly accurate approach and methodical record-keeping. All his resulting samples were preserved for further analysis by an independent party. He wrote a number of articles, some of the earliest on HPHT diamond, in which he claimed to have produced small diamonds. However, in 1928, he authorized Drive, Ch. Deesh to publish an article in which he stated his belief that no synthetic diamonds had been produced up to that date. He suggested that most diamonds that had been produced up to that point were likely synthetic spinel. Traditional diamond mining has led to human rights abuses in Africa and elsewhere. The 2006 Hollywood movie Blood Diamond helped to publicize the situation. Consumer demand for synthetic diamonds is increasing, albeit from a small base, as customers look for stones which are ethically sound and are cheaper. GE Diamond Project. In 1941, an agreement was made between the General Electric, Norton and Carborundum companies to further develop diamond synthesis. They were able to heat carbon to about 3000 degrees Celsius under a pressure of 3.5 gigapascals for a few seconds. Soon thereafter, the Second World War interrupted the project. It was resumed in 1951 at the Schenectady laboratories of GE, and a high-pressure diamond group was formed with Francis P. Bundy and H.M. Strong. Tracy Hall and others joined this project shortly thereafter. The Schenectady group improved on the anvils designed by Percy Bridgman, who received a Nobel Prize for his work in 1946. Bundy and Strong made the first improvements, then more were made by Hall. The GE team used tungsten carbide anvils within a hydraulic press to squeeze the carbonaceous sample held in a catlinite container, the finished grit being squeezed out of the container into a gasket. The team recorded diamond synthesis on one occasion, but the experiment could not be reproduced because of uncertain synthesis conditions, and the diamond was later shown to have been a natural diamond used as a seed. Hall achieved the first commercially successful synthesis of diamond on December 16, 1954, and this was announced on February 15, 1955. His breakthrough was using a belt press, which was capable of producing pressures above 10 gigapascals and temperatures above 2000 degrees Celsius. The press used a pyrophyllite container in which graphite was dissolved within molten nickel, cobalt or iron. Those metals acted as a solvent catalyst, which both dissolved carbon and accelerated its conversion into diamond. The largest diamond he produced was 0.15 millimeters across. It was too small and visually imperfect for jewelry, but usable in industrial abrasives. Hall's co-workers were able to replicate his work, and the discovery was published in the major journal Nature. He was the first person to grow a synthetic diamond with a reproducible, verifiable and well-documented process. He left GE in 1955, and 3 years later developed a new apparatus for the synthesis of diamond, a tetrahedral press with 4 anvils, to avoid violating a U.S. Department of Commerce secrecy order on the GE patent applications. Hall received the American Chemical Society Award for Creative Invention for his work in diamond synthesis. Later developments and independent diamond synthesis was achieved on February 16, 1953 in Stockholm by the ASEA, one of Sweden's major electrical manufacturing companies. Starting in 1949, ASEA employed a team of 5 scientists and engineers as part of a top-secret diamond-making project codenamed Quintus. The team used a bulky split-sphere apparatus designed by Baltzar von Platen and Anders Kamp. Pressure was maintained within the device at an estimated 8.4 gigapascals for an hour. A few small diamonds were produced, but not of gem quality or size. The work was not reported until the 1980s. During the 1980s, a new competitor emerged in Korea, a company named Ilgin Diamond. It was followed by hundreds of Chinese enterprises. Ilgin Diamond allegedly accomplished diamond synthesis in 1988 by misappropriating trade secrets from GE via a Korean former GE employee. Synthetic gem-quality diamond crystals were first produced in 1970 by GE, then reported in 1971. The first successes used a pyrophyllite tube seeded at each end with thin pieces of diamond. The graphite feed material was placed in the center and the metal solvent between the graphite and the seeds. The container was heated and the pressure was raised to about 5.5 gigapascals. The crystals grow as they flow from the center to the ends of the tube, and extending the length of the process produces larger crystals. Initially, a week-long growth process produced gem-quality stones of around 5 mm, and the process conditions had to be as stable as possible. The graphite feed was soon replaced by diamond grit because that allowed much better control of the shape of the final crystal. The first gem-quality stones were always yellow to brown in color because of contamination with nitrogen. Inclusions were common, especially plate-like ones from the nickel. Removing all nitrogen from the process by adding aluminium or titanium produced colorless, white stones, and removing the nitrogen and adding boron produced blue ones. Removing nitrogen also slowed the growth process and reduced the crystalline quality, so the process was normally run with nitrogen present. Although the GE stones and natural diamonds were chemically identical, their physical properties were not the same. The colorless stones produced strong fluorescence and phosphorescence under short-wavelength ultraviolet light, but were inert under long-wave UV. Among natural diamonds, only the rarer blue gems exhibit these properties. Unlike natural diamonds, all the GE stones showed strong yellow fluorescence under X-rays. The De Beers Diamond Research Laboratory has grown stones of up to 25 carats for research purposes. Stable HPHT conditions were kept for 6 weeks to grow high-quality diamonds of this size. For economic reasons, the growth of most synthetic diamonds is terminated when they reach a mass of 1 carat to 1.5 carats. In the 1950s, research started in the Soviet Union and the US on the growth of diamond by pyrolysis of hydrocarbon gases at the relatively low temperature of 800 degrees Celsius. This low-pressure process is known as chemical vapor deposition. William G. Eversole reportedly achieved vapor deposition of diamond over diamond substrate in 1953, but it was not reported until 1962. Diamond film deposition was independently reproduced by Angus and co-workers in 1968 and by Deryagan and Fedosiv in 1970. Whereas Eversole and Angus used large, expensive, single-crystal diamonds as substrates, Deryagan and Fedosiv succeeded in making diamond films on non-diamond materials, which led to massive research on inexpensive diamond coatings in the 1980s. In recent years, there has been a rise in cases of undisclosed synthetic diamond melee being found in set jewelry and within diamond parcels sold in the trade. Due to the relatively inexpensive cost of diamond melee, as well as relative lack of universal knowledge for identifying large quantities of melee efficiently, not all dealers have made an effort to test diamond melee to correctly identify whether it is of natural or man-made origin. However, international laboratories are now beginning to tackle the issue head-on, with significant improvements in synthetic melee identification being made.